Hello, this is Speaker Chen Dili. I'm from Institute of Computing Technology, Chinese Academy of Science. I will introduce our recent work, AutoTSMM, an auto-tiling framework for building high-performance tall and skinny matrix multiplications on CPUs. Let's start with the concept of GEM, General Matrix Multiplication. GEM is the heart of C++. It is widely used in scientific computing, deep learning, statistics, and many other domains. Vendors and the communities already optimize GEM on various platforms. There are many open source implementations, including Atlas, OpenBLAS, Bliss, and Eigen. Meanwhile, some vendor libraries like 1MKL, RMPL are provided on the specific platform. The formula of GEM as follows. A, B, and C are the input matrices. Alpha and beta are scalar numbers. C is the output matrix. So let's look at the conventional implementations of GEM. We decomposed the large matrix multiplications into panel-panel multiplication. Then it decomposed into block panel multiplications. And finally is slice times slice. And every time a smaller block is multiplied, it will be stored in a faster storage level. This is the key for reducing the data movement for GEM. Now let's talk about the motivation. We all know that neural networks are the foundation of deep learning. In deep learning frameworks like TensorFlow and 1DNN, most running time is spending on convolution layers. So it's important to optimize convolution, and many works have been done. Notice that these pictures are all from why GEM is at the heart of deep learning. The most famous algorithm is the image to calling algorithm, which is one of the most popular algorithms for optimizing convolution. Image to call transform the convolution to GEM to utilize optimized BLAS libraries and speed up neural networks. Convolutional GEM are targeting regular shaped matrix, which means M and N are relatively large, while K may be moderate. But the input sizes vary in different applications, and the input sizes are usually non-regular shaped. The convolutional kernels are usually small scale, and the input image are large scale. So the convolution will be transformed to a tall and skinny matrix multiplication. And sometimes the input matrix needs to be reused many times. Non-regular shaped GEM like TSMM is common in real-world deep learning applications. Unfortunately, the conventional GEM implementations are only optimized for regular shaped GEM and do not support data reuse. So what is the definition of the TSMM? TSMM is tall and skinny matrix multiplication. This picture shows what TSMM looks like. The n dimension will be significantly smaller than m and k dimension. TSMM is extensively used in applications like deep learning because of the image to calling algorithm. Inter 1MKL provides highly optimized TSMM on x86 platform, and Facebook already optimized it in their data centers. TSM2 and TSM2X discussed the TSMM optimization on NVIDIA GPUs. However, few works have been done to optimize TSMM on different CPUs. TSMM is one of the most important non-regular shaped multiplications. Conventional gem cannot reuse data. Data reuse is a key factor for optimized TSMM in real-world deep learning applications. So pre-packed TSMM reduces the packing overhead in conventional gem implementations, and it fulfills the need for data reuse. Our works focus on optimizing the pre-packed TSMM on mainstream CPUs, and it can benefit numerical libraries like NumPy for spinning up convolution layers. We summarize the challenges. First, no data reuse in conventional BLAS libraries. Second, no TSMM implementations on other mainstream CPUs except x86. Third, no efficient kernels on Kunpeng platforms because of the hardware flaws. Here are the main contribution of our works. First, we design a auto-tuning framework, AutoTSMM, for building high-performance TSMM on all mainstream CPUs. And the performance is competitive with the state-of-the-art TSMM implementation from Intel MKL, and outperforms all conventional GEM implementations on all platforms. Second, we analyze the shortcoming of the conventional GEM implementations on computing TSMM and propose a novel tiled strategy to implement high-performance TSMM on CPUs. Third, we analyze the poor performance of TSMM on the ARMv8 platform and implement high-performance assembly in the kernels on the ARMv8 platform. Tiling is the most effective way for building high-performance matrix multiplication on CPUs. So how to tile the TSMM? TSMM is decomposed into GEPB, which means panel block multiplication. MT is block height assigned for one thread. KC is blockwise suited for L2 catch. Since N is significantly smaller than M and K, the N dimension tiling algorithm will not be executed when N less than or equal to NC. Then GPB is decomposed into GPBT, which means panel block multiplication by each thread, where MC is block height suited for L2 catch size. Finally, the GBBT, which means block multiplication by each thread. It is computed as a unit by inner kernels. Catch block sizes are one of the key factors for optimizing GEM on modern CPUs. We have to use cache capacity as much as possible. The best performance of TSMM is achieved most likely when MC times KC is about half of the size of L2 catch. And KC times NC is equal to the size of L1 catch. We design a runtime predictive model to auto-tune TSMM based on the user input sizes. The predictive model based on these two equations, and it generates tile sizes. The search patterns depend on the selected inner kernels and the input, and the tile sizes are limited by these two formulas. Let's talk about the auto-tuning framework, AutoTSMM. AutoTSMM is divided into install time stage and the runtime stage. It selects the best inner kernels on the install time stage and generates the execution plan in the runtime stage. In the install time stage, the assembly kernel selector searches and selects the optimal inner kernels. Then it sends the kernel sizes into to the runtime stage. In the runtime stage, the catch block designer receives hardware features, and it generates the catch block strategy based on the hardware features and the inner kernel sizes. A predictive model searches the tiling space and creates the catch block strategy based on the catch capacity. The multi-thread optimizer generates the multi-thread strategy. The strategy are applied to the pre-packed modules. Note that the number of threads on n dimension is one of the most important factors for optimizing multi-threaded TSMM. Because n dimension is one of the smaller, it's much smaller than other dimensions, and assigning too many threads on n dimension is not a good idea. So it should be careful to deal with the multi-threading on n dimension. The performance evaluator, it measures the performance of the pre-packed modules, and finally, it selects the execution plan. This picture shows the different workflow of the conventional GIM and the pre-packed GIM. The difference is that we have to allocate memory space equal to the input matrices, and we can store them for future reuses. Matrix multiplication on CPUs are divided into two operations, packing operation and computing operation. Conventional GIM performs a tile algorithm that makes memory access continuous during the computation, and the performance can benefit from cache locality. The overhead of packing operation is negligible when computing regular shaped GIM, because it can be amortized in the computing operation. A conventional GIM can only achieve suboptimal performance when computing TSMM, because n dimension is too small and the packing operation cannot be amortized in computing operation. In addition, conventional GIM cannot reuse data because the packing operation and computing operation are coupled. So a pre-packed TSMM is necessary. Meanwhile, the plan will be repeatedly executed, so the overhead of AutoTSMM will be negligible. Then the right picture shows the multi-threaded pre-packed TSMM. We need an extra index space for every thread. The conventional GIM implementations usually assume the length of n is equal to m, and it will assign number of threads according to a fixed parameter. Thus, conventional GIM may over-assign threads on n dimension when computing TSMM. And the over-assignment causes too much thread synchronization overhead. In addition, the packing operation in conventional GIM implementations allocate temporary space to store continuous panel or blocks, and each thread store until other thread finished to prevent the temporary space from being overwritten. As for pre-packed TSMM, each thread can directly compute the tile matrix multiplication without thread synchronization, because every block has been packed into a new memory address. The pre-packed TSMM is a trade-off, but is effective when the data is reused. Cache complexity is a good approach to qualify the catch misses. It represents the number of catch misses the algorithm incurs. Here, the algorithm catch complexity of the naive three-loop gene and the conventional block gene and our pre-packed TSMM. You can see the novel multi-threaded tile algorithm we proposed is effective. This is block multiplication computed by inner kernels. The inner kernels perform a slice times slice matrix multiplication. MR and NR in the picture are the sizes suited for register blocking. The flaws on Kunpeng instruction issue unit makes the existing inner kernels can only achieve suboptimal performance. So we use register blocking, reordering instructions, and loop unrolling, and prefetching from the cache to optimize inner kernels on Kunpeng. This is our experimental environments. We implement AutoTSMM on both x86 and ARM v8 platforms, and we use G-flops for evaluation. The packing time is one of the most important factors. This figure shows packing time taken on the x86 and ARM v8 platforms. When n is very small, the percentage of the packing time is very large. With the increase of n, the percentage of the packing time gradually decreases. Our experimental results show the massive advantage of AutoTSMM. It outperforms MKL-TSMM and other conventional gene implementations from OpenBLAS, MKL, and Bliss. We can see when n equal to 240, the packing time taken is less than 20% on x86 platform. But AutoTSMM can still achieve a good acceleration compared to conventional gene implementations. It shows that our tile algorithms works well. From the curves, we can see first, AutoTSMM brings significantly speed up comparing to conventional gene implementations. Second, AutoTSMM and MKL-TSMM reduce the packing time by pre-pack operation and achieve a significantly speed up by the data reuse. And our runtime tile algorithm is effective, and it outperforms the inter-MKL on computing significant single precision TSMM and achieve competitive performance on computing double precision TSMM. This is because the double precision in the kernel is not as good as a single precision one. This is a multi-threaded performance comparison on ARM platforms. You can see AutoTSMM achieve huge performance improvement compared to OpenBLAS, ARM-PL, and Bliss. Now we can conclude that AutoTSMM is a portable auto-tunning framework to build the high-performance tall and skinny matrix multiplication on mainstream CPUs. And we proposed a high tile algorithm for TSMM. Our inner kernel implementation on ARM v8 platform is effective. We foresee that our method will achieve even better performance on other platforms like RISC-V. And we will focus on optimizing sparse TSMM. Thank you for listening. If you have any questions, feel free to contact me.